It is part 2 of section 4.3, higher order partial derivatives. In the first part, we studied partial derivatives. We can apply the derivatives more than once to get higher order partial derivatives. For functions of two variables, x and y, let's consider second partial derivatives. After getting f sub x, and we apply one more time an x-directional partial derivative to get f sub xx. Here, first we make x-directional derivative and one more time. So we can get here, we use this notation. And sometimes we are using this notation, f sub 1, Now, f sub xy means x first and y directional next. And also we can use this notation. Similarly, we can get f sub yx and f sub yy. Okay, let's try to get second partial derivatives of this function. Let's start with the first derivatives. Okay, f sub x, x-directional derivative for given function. This is 3x squared from the first term. And now that is 2x, and y will be considered as a constant, y cubed, so that must be 0. Okay, f sub y, y-directional derivative. Okay, this must be 0. That must be 3x squared and y squared. X cubed becomes now 3y squared after differentiation. Okay, for the last term, that is minus 4y. Okay, so we got first partial derivatives, and from here we can get second partial derivatives. For f sub x, we try to get one more time x-directional derivative. From here, now 6x, and that will be plus 2y cubed, right? Okay, now how about f sub x, y? For f sub x, we try to make y-directional derivative. That must be here now 6xy squared, right? That one. That becomes 3y squared. So that along with 2, it becomes 6. Right? Okay, now f sub y, and for that one, we make x derivative. Okay, so x direction, that will make 6 and x. Now y squared as constant, and that must be 0. How about f sub y, y? For that one, we make one more time y-directional derivative, which becomes here 6x squared y. Okay? And okay, we have one more term here, minus 4. Okay. So we got every second partial derivative. Here, these two are same. Now, it's not accidentally the same. In fact, and f sub xy and f sub yx are the same when they are continuous. So this one is really an important mathematical the theorem, and so that we can use this one later in computation. It means that once after derivative they are continuous, then the order of derivative is not important. Okay, that is the idea of the Clairaut theorem. F is defined on a disk that contains the point AB. If f sub xy and f sub yx are continuous on the domain, then at the point AB, f sub xy and f sub yx has the same value. These two functions will have the same value once they are continuous. Okay, that's the Clairaut theorem. So we can show these are the same when these third order partial derivatives are continuous. So the order of the derivatives is not important. It doesn't matter. You can get the result and with an arbitrary order once they are continuous. You can easily see in many cases if the derivatives are continuous. For this one, you can easily see that after derivative, it'll be continuous, right? Okay. So let's try to verify the theorem. Now f sub x, x derivative, okay, here. Now for this one, y e to the y, how about f sub y? That is, now x is constant and we have two appearance of y, so we have to use the product rule. For this one, now x e to the y. For that one, we have xy e to the y. Right? Now, from these first order partial derivatives, we can get the second order derivatives. Okay, so from f sub x, let's try to make y derivative. Okay, here. Then again, by using the product rule, we have e to the y plus y e to the y, right? Now how about f sub y and x? For that one, x derivative. Then from first one, we have e to the y. From second one, just we consider this as constant when we apply x derivative. So that will be y e to the y. So we have the same result. So we verified the theorem. Okay. Once the second derivatives are continuous, then the order of derivative differentiation is not important. Yes, always you can get always the same result. Okay. Okay, we want to calculate f sub xy zx given here that one. So we can easily see this fourth order derivatives must be continuous. So we may apply the differentiation with an arbitrary order rather than x, y, z, x. Keeping the order, we can apply. So we may do this way. And that must be same as f sub xx, x first, twice, and then y and z, right? Okay. The reason is that rather than some extra here variable going out, just the constant multiplication is better. So that's the reason we try to get x twice differentiation. Okay. Okay. Now f sub x, that is now cosine 3x plus yz, and 3 will appear here. One more time, from this one x derivative, then one more 3 will come out, and cosine will change to sine, minus sign. so that the coefficients must be minus 9 and sine of 3x plus yc. Right? How about here now, f sub xx and y directional derivative. And then this one will be changed to cosine, and y derivative will make z go out. So minus 9z cosine here 3x plus yz. Okay. Now, finally, we have to apply z derivative f sub xx y z. Now, for z, we have twice appearance, so that we have to use product rule. So along with this one, now minus 9 cosine 3x plus yz. And for that one, here, okay, that'll be changed into minus sign, so that this negative will disappear. So it's changed into positive. And for this block, z derivative will make y coming out. So that here we have, that is 9 yz and sine and the block. Okay, 3x plus yz. Right? Okay, that's the final answer. Okay, that's the end of the section. Okay, we'll see one problem here. In this problem, you are asked to find the f and s partial derivatives f sub x and f sub y, to find them, to figure out f and f sub x, f sub y graphs. You may assume one of them is the graph of f. For example, if you assume a is the graph of f, then now let's see x directional derivative. So x is increasing in that direction, which means that around there, f sub x must be positive because it's increasing in x direction. So that, okay. So in fact, on the bottom, that position, right, around there, so that it is increasing in x direction. And so the x derivative must be positive. Now here is not positive, there is not positive. That means it cannot be the graph of f. Now you may assume here if now b is the graph of f, then you may try to figure out. In this way, you can find you can determine the graphs. Okay? Okay, thank you.